In section 3.2, we actually learn what a linear programming problem is and learn how to formulate them. So your textbook's definition of a linear programming problem states it consists of a linear objective function to be maximized or minimized, subject to certain constraints in the form of a linear inequalities or equations. And we'll use linear inequalities in our class. What we're going to do in this section is learn how to formulate them, and then in the next section, we'll learn how to solve them. So basically, these are our steps that we're going to follow. So the very first step is to define your variables. And for us, we'll use an X and a Y. And so X might represent a model A that we're producing, and Y might represent a model B that we're producing of some objects. Printers, fireplace grates, barbecues. Okay, once you've done that, the next thing you're gonna do is define or write the objective function. And our objective is either going to be maximize profit, the revenue that you're bringing in, or we might be minimizing the cost associated with producing. So you're going to do one or the other, not both. After you've done that, the next thing you're going to write is your linear constraints. So we'll write these are the constraints that are binding what you're doing. They're restricting what you do. And it might be how much plastic you have on hand in order to produce something, or how many labor hours you have to produce something, or how much cost you have to produce something. So it's things that are going to constrain how much you can do. And that's really where we're done in this section. Then in the next section, we're going to come back in and graph the constraints. And identify the feasible region. Which we somewhat have already done. Step 5, you're then going to come in and locate the corner points, which we have not done yet. Your textbook refers to those corner points as vertices. And those are the corner points of that feasible region. And again, we'll talk about this when we go to do it in the next section. And then find the optimal solution. And that's what your textbook does. So in this section, we'll address the first 3, and the next section will address the next 3. So let's jump into it by doing an example. So this is example 1. We will come back and use this same example in the next section to do the remaining part of the linear programming problem. Okay. So example 1, it's a maximization problem. A division of the Winston Furniture Company manufactures dining tables and chairs. Each table requires 40 board feet of wood and 3 labor hours. Each chair requires 16 board feet of wood and 4 labor hours. The profit for each table is $45, while the profit for each chair is $20. In a certain week, the company has 3,200 board feet of wood available and 520 labor hours. How many tables and chairs should Winston manufacture to maximize its profit? Again, what we want to do is formulate, but not solve. So to help us organize what's going on, I'm going to use a little bit of a table just to organize information and show you where the information is coming from. So we're making tables, dining tables. We're also going to make chairs. And that's what we produce in our business. Okay, it goes on to tell me that each table requires 40 board feet. So I'm going to label this column as board feet, meaning wood. And we know that it takes 40. And 3 labor hours. So I'm going to go into another column and label that as my labor hours. We know that each chair requires 16 board feet and 4 labor hours. It then goes on to tell me that the profit, so here's more information, another column, for each table is $45 and for each chair is $20. In a certain week, we know that we have 3,200 board feet available. So board feet, that's a total amount. That's going to go over here. And we also have 520 labor hours. And what we want to do is maximize this column. So that's just the information. Okay, so if you remember our 3 steps, the very first step we're going to do is come in and define our variables. So step 1, we're going to define. We're going to let X be the number of tables that we're going to produce in a week. And we're going to let Y be the number of chairs that we're producing in a week. You're saying, well, why don't the chairs and the tables match up? Because sometimes people break chairs or buy extra chairs or not, a smaller amount of chairs. So it's not sold as a set. So there's our definition of our variables. Step 2, we're going to come in and write our objective function. So our objective function in this case is to maximize our profit. So maximize is what our objective is. P is where we're going to start a function. Well, what is our profit? Well, for every single table we make $45. So if I take 45 times the number of tables, I'll figure out how much I'm making off my tables. And then do the same thing with the number of chairs and write that as a 20 times the Y. And that's our objective function. So step 3 is our linear constraints. And so what we use here is we use the words subject to. So it's subject to the following constraints that are restricting us on what we've got. So one of my constraints is going to be from the number of board feet that I have available. So I know every table takes 40 board feet. Every chair takes 16 board feet. And I can't go over what's available in a week, which is that 3,200. So less than or equal to 3,200. And there's our first linear constraint. Again, they're linear because they're lines. Our second one's going to come from the labor hours. And I know that because this is where the total is in these 2 first columns. So our labor hours are going to be 3x plus 4y. So 3 times the number of tables, 4 times the number of chairs, and we have to stay inside that 520. So less than or equal to 520. And then we tack on, because we always want to make a positive amount of tables. X is greater than or equal to 0, and Y is greater than or equal to 0. And that's the formulation of our linear programming problem. We defined our variables, we stated our objective, and we have our constraints.